Greetings. In this video, we're going to talk about linear approximations, or the tangent line approximation to a function at a given point, right? At a given value of x. So here I have graphed some generic function, and what I need is a particular point. Let's label this point here x equals a. And I'm going to draw the tangent line to this graph, to this function, at x equals a. So I'm going to do that in yellow. It's going to look something like this, right? Okay. So we know how to find the tangent line. The slope of the tangent line, of course, which I'll call m, is just the derivative of the function at x equals a, right? And I want to emphasize the fact that the derivative of a function is a local property. So what I mean by local is that the derivative at x equals a only really makes sense when you're very close to a. Right? If you're in some small region near A. This is sometimes called a neighborhood of A. Neighborhood of A. So they're just values of x that are near A. If you like, it could be a delta interval, right? So a plus delta, a minus delta. But let's not get into that, right? As long as x is somewhere near a, the derivative could be an approximation to the function itself. Right? What do I mean by that? So if I take this region around x equals a and go up to the function, so I'm going to take this little area here and magnify it, right? I'm going to kind of blow this up, right, so that we see this a little bit better. So in this region, the function looks oops, I should use the same color. Sorry, here we go. So the function looks something like this, and the tangent line, so here's x equals a, looks something like this. And yeah, so you can see that there's not much difference between the function in green, that's the original function f of x, and the tangent line, which the book calls L of x, and I think that's a good name for it because it's a linear function. So L for linear, right? Right. So as long as you're near x equals a, the tangent line approximates the function itself, right? Now, why do we have to be in a neighborhood of a? Why do we have to be, in a local region around a? So you can see on the graph here that the function, if you go farther away from a, this is the tangent line. That should be a line, something like this, is a pretty poor approximation to the function, right? So yeah, if x is, let's say, this number here, let's call it c, you can see that this is f of c, and you can see way down here is L of c, and you can see they're pretty far apart, right? I mean, one's positive, one is negative, and they're not even close. So yeah, the further away you get from x equals a, the worse the approximation is. Okay? Conversely, the closer you are to a, the better the approximation, right? If I can get even closer to a and just look at this region here, and you can see that there's just a very tiny difference between L of x, the approximation, and f of x, the original function. Okay, so the first thing we want to do is write down L of x, right, as a function of x, right? So we know that this, sorry, I'm supposed to use a different color here. So, yeah. Okay, sorry about that. So L of x is the linear approximation, right? And yeah, ultimately, we want to write this as the equation of a line, right? So mx plus b. But you might also remember another way to write the equation of a line. So if we want the equation of a line that passes through a given point, right? Say x1, y1. And let's say we know the slope is m. That's all we need to determine a line, right? You either need 2 points, right, which determines the slope, or if you know the slope, you need 1 point to determine the line, right? So the equation can be written as y minus y1 equals m times x minus x1. Right, so this is sometimes referred to as the point slope form of a line, of the equation of a line. Right? After all, you have a point and you have the slope, and that's all you need to determine the equation. Right? So I'm going to use this version of the line to derive the linear approximation. Right? Right. So first of all, what is our slope? Right? Our slope, m, remember, to get the slope of the tangent line, you need the derivative. It's, right, f prime of a. So, right, you take the derivative of the original function, and then you plug in whatever number a is, right? And that gives you the slope, right, as a number. All right, so what else do we need? We need a point, right? And the point that we have, right, instead of x1, I'm using the letter a. So x1 is just the number a, right? And then y1 is the corresponding y value of a. On the graph, it's over here. So if this is x equals a, then y is going to be f evaluated at a. Right? So my y1 is really just f of a. Right? Not f prime, right? That's the slope. It's just f of a, the y coordinate, right? So plugging all this into the point slope form, I get that y minus y1, which is f of a, is equal to m, which is f prime of a, times x minus x1, but remember x1 is a. Right? And now if I want to write it in y equals mx plus b form, I just have to add f of a to both sides. Let's see if I can do that. Plus f of a plus f of a. So my equation will be y equals, again, m is just f prime of a, times x minus a plus f of a. Right. And that is what the book calls L of x, right? This is the linear approximation to the function near a. So L of x is f prime of a times x minus a plus f of a. Right. Good to know. So this is the linear approximation or sometimes we'll call it the tangent line approximation to the function f near a. Right? And so what I mean by that is we can approximate f of x using L of x, but only when x is near a, right, or close to a. And now, you might ask the question, well, what do I mean by near a, right? How close does x have to be to a? Well, it depends on a couple things, right? It depends on your function, right? And it depends on a, right? I mean, you can imagine a function having a sharper bend to it, right? So something like this, which I still want to be smooth, right? I don't want a complete corner like this. Because if I have a corner or a cusp, remember at that point, f prime of a does not exist, right? There's no derivative when you have a corner like this. And then it's meaningless to even talk about the tangent line approximation at such a cusp, because if there is no derivative here, then there's no slope, right? So L of x, right, just wouldn't exist at a cusp. But as long as your function is smooth enough, right, you can talk about the tangent line approximation, say at this point here, right? And then you can see that you really have to be very close to a here, because if I pick this to be my neighborhood, then you can see if I'm even just a little bit away, the difference is going to be pretty stark, right? So yeah, so you have to be even closer to get a good approximation. So yeah, it depends on the function, and it also depends on the behavior of the function near the point x equals a. So in most cases, right, near a is good enough. We don't have to get into the the delta neighborhoods and all that at this point. Okay, so let's look at an example. Again, I'll start with a simple one. Okay, so let's start with f of x is just x squared, right? And we want to find L of x for a equals 3. All right. Well, L of x is just f prime of a times x minus a plus f of a. And since we're given a is 3, let's first find f of a. All right. F of a is f of 3, which is just 3 squared, which is 9. Okay, good enough. What else do we need? We also need f prime of a. So we have to take the derivative. And I won't bore you with the details, but you should know the derivative is, of course, just 2x by the power rule. And then plugging in a equals 3, we get 2 times 3 is 6, right? So that's the slope of the tangent line at x equals 3. Okay, so I think we have it. Just plug in all the numbers, right? F prime of a is equal to 6 times x minus a is 3, plus f of a, which we said was f of 3 is 9. So plus 9. Right? And then it just might help to multiply all this out. We get 6 times x minus 6 times 3 is 18. And negative 18 plus 9 is just negative 9. So my L of x is just 6x minus 9. Right. And again, if it helps, you can just draw the graph. It's just going to be a little sloppy this time. So let's start with f of x, which is x squared. I'm going to sort of exaggerate a little bit. So pretend this is y equals x squared. And I'm going to place my a right about here. Right. So again, this is not to scale, because then the y value we know is 9. 3 squared is 9. And then for the tangent line, which again I'll do in yellow. Oops. So that'll be my L of x, and we know the slope is 6. Right, and we know the equation is y equals 6x minus 9. So what that means is the y-intercept would be way down here at 0, negative 9. Okay. All right, so let's just see how good of an approximation this is. For example, we know that f of 2 is 4, right? 2 squared is 4. So what would L of 2 be? If I plugged in x equals 2 into L, we get 6 times 2 minus 9, which is 12 minus 9 is 3. Right? So yeah, we get 3 instead of 4. So not great, but still, I mean, it's close, right? Yeah, and you can see on the graph that's it's kind of hard to tell because right here would be 3, right? So yeah, I'm off by 1. Right? But remember, that's just because 3 is, or x equals 2 is probably not all that close to x equals 3, but I can get closer. So for example, if I plug into the original function 2.8, right, I get 2.8 squared, which is 7.84. And now let's compare that to the approximate results. So if I plug in 2.8 into L, that's 6 times 2.8 minus 9, which is 7.8. So yeah, now compare that to the actual answer, 7.84. You can see that's awfully close, right? You're off by 0.04. So that's pretty good, right? And you can see that the closer you get, it's even better. If you want to do one more example, let's do one a little bit bigger than 3. Let's do 3.04. So if I square 3.04, I get 9.2416. Right. Yep, let's not round. Let's keep everything exact here. And now plug that into the linear approximation. So I get 6 times 3.04 minus 9. Which is 9.24. Right? So at this point, you can see the difference is very tiny. 0.0016 is the difference. So yes, and again, that's because 3.04 is very close to 3. Right. Okay, so that's the idea, right? As long as we're near x equals 3, we're using the tangent line to approximate the function x squared. Okay, let's do another example. Okay, so now f of x is cosine of x, and we want to find the tangent line approximation, the linear approximation, at a equals 3. All right, so let's write down the linear approximation again. It's just f prime of a times x minus a plus f of a. And in this case, a is pi over 3, right, which is 60 degrees, but we're going to stick with radians, right? And I want to keep pi over 3 exact, right? I mean, we can approximate it by 1 point something, right? 1.0472, let's say. Yeah, 1.0472. Right, but let's not do that yet. Oop, that's a 0, not a 6. Okay, so what do we have? We have first of all, what do we need? We need f of a. So that's f of pi over 3, which is cosine of pi over 3, which is 1/2. Again, that's one I know by heart. You know, hopefully you don't have to plug that in a calculator, but well, if you do, you'll get 1/2. And then the derivative of cosine we know is negative sine. So plugging in, pi over 3, that's the a, we get negative sine of pi over 3, right, which is going to be negative square root of 3 over 2, which I think is about negative 0.0866, if I remember right. Right, but for now, we're going to leave it as exact, negative square root of 3 over 2. Right, which begs the question, if L of x is just an approximation anyway, why aren't we using the approximate values, which is a fair question. You could, right? You can just use decimals everywhere here. But when we write the approximation, remember, we're treating L of x as a linear approximation. You can find the exact value of the approximation, right? If that even makes sense, right? And then we'll find the approximate value of the approximation. All right, so L of x then is just going to be f prime of pi over 3, which we said is negative square root of 3 over 2, times x minus a being pi over 3, plus f of a was 1/2, right? F of pi over 3. Right, and again, we want to distribute the slope here, so this is negative root 3 over 2 times x, and then plus, I'll put pi times the square root of 3 over 2 times 3 is 6, plus 1/2. So yeah, this is my m, and this is my b. So this is just in the form y equals mx plus b. Right, just to make that official. And if you're worried that b is the sum of two numbers here, I mean, it's just a number. If you want to get a common denominator, just multiply top and bottom by 3. Times x, and then we can write b as 1 fraction pi square root of 3 plus 3. Right, so now this is my b, and this is my m. Okay, so there we go, right? That's our linear approximation. So remember, this is going to represent an approximation of cosine of x, but only when we're near pi over 3, right? When we're near 60 degrees. Okay. Okay, so let's see how good of an approximation this is. So let me pick x equals, how about just 30 degrees, right? Pi over 6. Right? So we know, f of pi over 6, cosine of 30 degrees, cosine of pi over 6, is the square root of 3 over 2. Right? So approximately that's the 0.866. Right. Now let's see what the approximation tells us. What is L of pi over 6? Well, it's negative square root of 3 over 2 times pi over 6 plus, and then this number, pi square root of 3 plus 3 all over 6. So you plug all this in your calculator, right? Again, you can think of this as the exact version of the approximation, but the approximate version of the approximation. So my calculator says that this is about 0.953. So not too bad, but not great either, right? I mean, we're off by, I think, less than 0.1. And you can calculate the percent error here. That might be more helpful as opposed to the actual error. And it is pretty close to 10%. Slightly higher than 10% here. So it's about a 10% error. So like I say, not bad, but not too good either. So let's get even closer. Right? Suppose my x now is, let's do 62 degrees. So in radians, that would be 31 pi over 90 exactly, or approximately 1.0821. Yeah, I'll keep 4 decimal places now. Okay, so that's my x, right? So what is f of x? And I guess I'll just use 62 degrees. So if you do this on your calculator, make sure you switch to degree mode. And now the cosine of 62 degrees is approximately 0.4695 to 4 decimal places. Good enough. Okay, so that's the exact answer, right? What is the linear approximation? Okay, so negative square root of 3 over 2 times x. Now, you can't use 62 here, right? Because this has to be in radians. So, yep, let's use the 4 decimal approximation, 1.0821, and then plus this number here, whatever the approximate answer this is here. So just plug all that in your calculator, and that gives us 0.4698, right? And you can see we're off by a little bit in the 4th decimal place, right? And so the percent error, so I get about 0.00064. So 0.064%. So less than 1/10 of 1%. Right, so that is an excellent approximation. And that's usually what happens when you plug in a number close to the original A. Okay. Okay, so your turn. Try this one. Right, so for my f of x, I'll use the rational function x over x plus 2. And you want to find L of x at x equals 1. And then we'll try this at at a equals 1. Well, same thing, right? But okay, so this should be an a at a equals 1. And then plug in x equals 1.5 into the original function f, and then plug it into the linear approximation. Okay, everyone all set? All right, so the linear approximation is, yet again, f prime of a, x minus a, plus f of a. So in this case, when a is 1, this is going to be f prime of 1 times x minus 1 plus f of 1. So f of 1, of course, is 1 over 1 plus 2, 1/3. And the derivative of x over x plus 2, so you probably want to use the quotient rule. You should get 2 over x plus 2 squared. And then plugging in 1, you get 2 over 1 plus 2 squared. 3 squared is 9. So 2 over 9 for the slope. So L of x is going to be 2 over 9 times x minus 1 plus 1/3. And expanding that out, you get 2 over 9 times x plus 1 over 9. Right? Or maybe better yet, you can just write it as a single fraction, right? 2x plus 1 all over 9. Okay, so that is my linear approximation. Remember that this is going to approximate f of x, which is x over x plus 2. Okay. Right, so now just plug in the numbers, right? For my f of 1.5, well, this will be 1.5 over 1.5 plus 2. So I can do this by hand here. So this is 3 over 2 plus 4 over 2. So 3 over 2 divided by 7 over 2 is going to be 3 over 7. Okay. So again, that's the exact value. Now, what's the approximate value? What is my L of 1.5? So this will be 2 times 1.5 plus 1 over 9. So that's going to be 3 plus 1 over 9, so 4 over 9. Okay, so what is the percent error? I know I didn't ask that, but it's reasonable to ask, right, how close are these two numbers? And for that, I think I'll just use the calculator. But it's what I'm just calculating is the difference in the two values, 4 over 9 minus 3 over 7, whichever one is bigger, an absolute value divided by 3 over 7. So it's about 3.7%, right? 0.037. So we're off about less than 4%, which is pretty good, right? So, right, and remember, 1.5 is pretty close to 1. But, you know, relatively speaking, it's not that close, right? We could have done this for, you know, x equals 1.05. And you'll see the percent error should go way down. All right, so that's it for linear approximations. Right. So to close, let's just talk about what happens when you change x by a little bit. Right. So here's a graph of some generic function, f of x, at some generic point a. Right. So we know if we go straight across, that the y-coordinate here will be f of a. And now I want to travel some distance away from a, right? And I can go in either direction, right? I can go to the left, but I think I'm going to go to the right, say by this much, and I'll call that just delta x, some small change in x, right? So now I come to this new point. This is a plus delta x. Right? And we can calculate the y-coordinate at this point exactly. We just plug that into the original function. And what we get is f evaluated at a plus delta x. Right? You can think of that as just the y-coordinate. I'll call this y1. Right? Well, if this is x1, then this will be y1, right? Okay. Now, if we use the tangent line approximation, the tangent line will look something like this. It's not completely straight, but close enough, right? So this is my L of x. Again, just to remind you, that's your f prime of a times x minus a plus f of a, right? So yeah, when I change my x, I get a change in y, which is just this, right? So this here will be my delta y, and it's just the difference in the two y values, right? It's essentially y1 minus f of a. So it's going to be f of a plus delta x minus f of a. Okay, so that's delta y, right? My delta x, on the other hand, my approximate change in y is what you get when you, I'm using the wrong color here. Let's use purple. So if I use this as my y-coordinate, which is L, right, evaluated at x1, or a plus delta a, you can see, right, that's the approximate y value. I get a slightly smaller difference, which we're going to call dy, right? So dy is, sorry, it's just f prime of a times delta x, right? How do I get that? Well, remember that, right, that the slope is f prime of a, and this is just rise over run, right? So the rise is the dy, and the run is the change in x. That's what we're calling delta x. I really should call it dx, shouldn't I? Right? So yeah, delta x is the same as dx. We're using the same thing here, right? So yeah, I probably should write this instead of delta x, I should use dx in this case. There we go. Okay, so dx and delta x are the same thing here. Let me emphasize that. Delta x and dx are exactly the same. However, delta y and dy are not the same, right? So remember, what is delta y? Delta y was defined to be f of a plus delta x minus f of a. Well, I could use dx here too, right? Same thing. Minus f of a, right? And so that's this difference in y's right here, right? On the other hand, the dy is f prime of a times dx, and that's this difference here, right? So you can see they're not exactly the same. Right, they're close, but they're not exactly the same. And so we can write that dy is an approximation to delta y, but it's not exactly the same thing, right? And it depends on how big delta x is, right? If delta x is bigger, you can see that the difference, the error, is going to be much greater, say over here, than over here, where it's pretty small. Okay. So dy is an approximation to delta y, right, as long as the delta x is pretty small. Right. And again, I'll put small in quotes because we don't know how small that is, right? Small enough. Right. And just as a quick illustration, let's go back to our first example where the function was f of x, which was just x squared, and we set a equal to 3, and we found that the linear approximation, which I'll write in yellow again, was 6x minus 9. Right, so this is approximately x squared when we're near x equals 3. Okay. So let me come up with a delta x. Right, so suppose we use delta x equals, let's, something small. How about 1/2? I'm not sure we did that one already, but okay. Yeah, delta x is just 1/2, right? So that means my a plus delta x is 3 plus 1/2, right? So 7 over 2, or 3.5. Right, so to calculate delta y, right, I plug in 3.5 into f, and I subtract f of 3. Right, so that's the difference in the height between these two values. And that's 12.25 minus 9. Right, so that should be 3.25. Okay, now to find dy, right, dy is defined to be, right, f prime of a, here a is 3, times dx, which is the same as delta x, right? So remember, f prime of 3, well, right, f prime of x was 2 times x, right, the derivative of x squared. So f prime of 3 is, again, 6, right? 2 times 3 is 6. So this is 6 times dx, again, same as delta x, 1/2. So 6 times 1/2 is 3, right? Which is approximately, right, 3.25. Obviously not the same thing, but that's exactly why we said that dy and delta y are not exactly the same, but they are approximate. And then one last thing before we go is to mention what this dy is. This dy is sometimes called a differential. Right? So the differential of y is just dy, and it's really just the derivative of the function times dx. Right? And you can think about just what the derivative of f is, f prime of x. It can also be written as dy dx, right? And so if I just multiply both sides by dx, right, and then just writing it in the correct order here, I get that dy is equal to, well, dx times f prime of x, but I'll write the f prime of x first, times dx. Okay, so let's just do some examples of calculating differentials. It's really just calculating derivatives. Okay, let's start with, we want to find dy for y equals secant of 4x. Right? So remember, dy is just the derivative, f prime of x times dx. So all we have to find is the derivative of y, and then just multiply by the dx, right? So if you remember, the derivative of secant is secant times tangent. Right? Don't forget the chain rule. Right? You have to take the derivative of 4x, which is just 4, and I'll pull the 4 in front. So 4 secant 4x tangent 4x. But that's not dy, that's dy by dx. So multiply by dx. And so dy is just going to be 4 times secant of 4x times tangent of 4x times dx. Right. Right. So nothing new. The only thing new is, right, dy is just the derivative times dx. So I'll let you try one. All right, so find dy. All right, dy if y is equal to the square root of x plus 1 over x minus 1. Right, all under the square root. Got it? Well, right, first just take the derivative. And to do that, you could do this a couple of ways. You can split this up and use the quotient rule, or you can think of this as x plus 1 over x minus 1 to the power 1/2, and then just use the power rule. This is just a good review of taking derivatives. Right? And then don't forget, this is the important part, the chain rule. We still have to multiply by the derivative of x plus 1 over x minus 1. So that's just the quotient rule. In fact, before we do that, let's write the first part here as 1/2 times the square root of x minus 1 over x plus 1. Remember, it's negative exponent means you take the reciprocal. Right. And now, for the quotient rule, we have the square of the denominator and the denominator. So low d high minus high d low. Right. So 1/2 square root of x minus 1 over x plus 1 times, so we have x minus 1, just to clarify, x minus 1 minus x minus 1. So I think we get negative 2 over x minus 1 squared. Right, and then we can simplify this even further, right? We have 1/2 times negative 2 is just negative 1. And the numerator here is x minus 1 to the 1/2. The denominator is x plus 1 to the 1/2. And the denominator here is x minus 1 squared. So we can just write this simply as negative 1 over, x plus 1 to the 1/2. And this will be x minus 1 to the 3/2. And maybe we should even just use negative exponents, right? So negative x plus 1 to the negative 1/2 times x minus 1 to the negative 3/2. Right? So that's y prime, the derivative. But the question was to write dy, so it's just all of that times dx. Okay. So that's dy. Negative x plus 1 to the negative 1/2 times x minus 1 to the negative 3/2 times dx. And as for the meaning behind what is dy, what is dx, so whatever this function f of x looks like, right, at a given value of x, right, if this is my dx, then my dy is gotten by the tangent line. Oops, let me draw the tangent line here. A little bit sloppy. Let's try that again. Okay. Right. So, yeah, so this is my dy, whereas the delta y is the difference from here to here, right? Okay, good. So again, it's maybe not a good approximation in this case, but it just, it's because the dx is too large. If the dx were smaller, then the dy is a much better approximation to the delta y. Okay, I hope this helps.